Good morning. Welcome to this course on Illumination Engineering and Electric Utility Services. Today we take up lesson 2 of this course. The lesson is to do with radiation, and the instructional objectives for this particular lecture are the ability to state the visible range of light, 2. State the range of light human eye responds to, and define what is a UV radiation, what is IR radiation, and understand and able to list the physical phenomena employed in artificial lighting, and understand the concept of color temperature and what it is. If you recall, in the last lecture we had already seen the need for the lighting, and we did mention that the human life very much depends on light, and more than 85% of information is acquired through our eyes, which requires light, and sun is the most potent natural source of light, and any efforts to make our environment lighted through artificial means is to make it as close to sun as far as possible using optimum resources at economic prices. We have also seen in that lecture that most of the artificial sources employ some form of electrical energy, and therefore we had a look at the preliminaries of what constitutes a electrical power system, and this has been dealt with in complete details. We saw the various ways the power is distributed, and we realize that most of the power transmission is AC in nature, which could be balanced or unbalanced, and three-phase in nature, which means there are two different kinds of connections that are employed, one delta, other star. We have understood what is meant by line and phase quantities and the use of overhead lines and underground cables for power transmission. So we begin today to look at a little more onto the phenomena of light or the physics of light. Hence the chapter or the lesson is titled radiation. By definition, light is that radiant energy which provides visual sensation in eyes. Once again, it should be re-emphasized that the eyes are one sense of organs which acquire more than 85% of the information that a human being acquires, and therefore the visual sensation is provided by the light is in the form of a radiation, and it is akin to radiant heat, but the frequencies and wavelengths are different. In that sense, light is also a form of electromagnetic energy. Now, it must be mentioned here that the visual light or visible light spans over the wavelengths 180 nanometers to about 1500 nanometers. This should be there should be a small correction here. It has to be 1500 nanometers as against 500 what is mentioned in the slide. And we also look at how the human eye responds to the visible light. Though visible light has a spectrum spread over 180 to 1500 nanometers, the eye responds over the spectrum spreading over 380 to 700 nanometers. The 380 nanometers corresponds to the violet color light, and 700 nanometer corresponds to the red. In fact, if we pass the natural light obtained, we know that the natural source of light is sunlight. Passed through a prism, we can see the beam splitting into various colors spanning from red to violet, corresponding to various wavelengths. On one extreme, one finds red color light of 700 nanometer wavelength, and the other extreme is the violet color light 380 nanometers. In fact, this is the spectrum one finds in a rainbow and oftentimes the children are taught this consists of VIBGYOR, meaning violet, indigo, blue, green, yellow, orange, red. In a subsequent lecture, we will look at more ways of quantifying these colors and looking at. So, in this lecture what we do, we look at how the light has different colors, what are the energy contents, how the eye responds, and these will be looked into. And then look at some of the physical processes that can be used to produce similar effect from artificial sources. So, here we have a diagram which shows relative energy due to sunlight in the visible spectrum. As may be seen, the x-axis is the wavelength of the electromagnetic spectrum, or lambda. We find two vertical lines drawn, one at 380 nanometers corresponding to violet and the other around 800 nanometers corresponding to red. The spectrum spreading over this region is what we call visible spectrum. As may be seen, in the mid region the relative energy is a maximum, and this spans over 500 to 600 nanometers, falling in the green yellow region. We have a region whose wavelength is less than the wavelength corresponding to violet. That is what we call as ultraviolet, and the frequency and the wavelength are inversely related. It must be mentioned here that being an electromagnetic spectrum, it propagates at the same velocity as the velocity of light in free space, which is 300 meters per microsecond. Therefore, lower the wavelength, higher is the frequency, and therefore we find ultraviolet has a frequency of excitation or electromagnetic frequency, spectrum frequency, higher than that corresponding to violet, and this is referred to as ultraviolet light. Therefore, the light spectrum, as can be seen, is ultraviolet, visible spectrum. Then we have a third spectrum which is having wavelength more than that corresponding to red, or lambda greater than lambda red, which is marked in this diagram as IR, meaning infrared. If you see carefully, infra means smaller than. That means the spectrum radiation which has frequency less than that corresponding to red light is what is called infrared. All of us are aware of the usage of infrared lamps for healing wounds, and that's one of the thing. In fact, in the slide it is mentioned the soplic, that should have been theroptic. That is the error in the slide, spelling mistake. It must be theroptic. And there are applications in the area of drying, heating and theroptic purposes using IR. In fact, certain discharge phenomena like lightning, when needs to be photographed, infrared cameras are employed. So, what do we see? We see the energy content of sunlight is a maximum in the green yellow region, spreading between 500 to 600 nanometers, and the whole spectrum of light can be divided into three zones. One is UV, having lambda less than lambda violet, visible spectrum spanning from 380 to 800 nanometers, and IR or infrared greater than 800 nanometers. Incidentally, UV is used for germicidal applications, and all of us are familiar the AquaGuard, which is used for getting the pure water these days. So, knowing about the relative energy, it is necessary for us to see how our eye responds, and that is termed in terms of a relative luminosity. The curve here, as has been in the previous curve, we have drawn the wavelength along the x-axis and relative luminosity, that is ability of eye to respond to the incident light. That is what we mean by luminosity. And as can be seen from the previous figure, you can recall the maximum energy content was in the green yellow zone. In a similar way, the response of the human eye is a maxima in the green yellow zone, and therefore with respect to that, how the eye responds to various light spectrum is what is seen in this particular curve. Let us see how we can use this to arrive at various lighting sources. Now, the artificial sources, as we are all aware, all of us have been using one form of the source or the other. Remember, unlike the prehistoric man, our activities are not curtailed with sunset or do not begin with sunrise. We are in a zone, in a time period where we work 24/7, that is all the 24 hours round the week, that is round the clock, round the week. Incandescent lamps are one of the foremost sources that have been used. They depend on the temperature of the filaments, and they are known to produce what is called as a continuous spectrum, as we saw in the radiation due to sunlight. Then you have gas discharge lamps, which are known to produce a discontinuous or line band. They do not produce a continuous spectrum like the sunlight. That means they radiate light at specific frequencies, and depending on the majority of the energy lying in a particular color, we refer to the discharge to be of that color. Then this is the two broad categories. So one needs to look at the spectral energy. What you can see in this figure is, as has been in all the figures, we draw the wavelength of the radiant light along the x-axis. There are about 4 curves. If you see, the first curve is to do with the energy content due to noon sun. The second curve is due to the tungsten lamp, and third one is due to blue sky. Now one may look at, with respect to, if you see the noon times sun, if you consider that as a base, you find that over the entire spectrum spanning from violet to red, it's more or less same throughout. On the other hand, that due to blue sky is peaking around somewhere between 400 to 500 nanometers, whereas that due to tungsten lamp peaks around the red. It is increasing from violet up to red. And in fact, to have an idea of how this relative spectral energy can be utilized, the response curve of the eye is also drawn here, which we said is the luminosity, taking the maximum response, which is the green light, as the base, relative luminosity curve, which is peaking around green corresponding to 550 nanometers, is seen. So what does it mean? It means that though blue sky has a peak energy around 425 to 450 nanometers, the eye is unable to respond, and therefore it is of no use. So this is one thing which has to be kept in mind. If you see this diagram, there are 3 particular things have been considered. 1, the all-pervading source, sunlight. 2, blue sky, essentially is a sky when the sun is partially blocked, could be clouded sky. 3rd is an artificial source used employing a tungsten filament. that is the incandescent lamp, as already told, it emits radiation based on the temperature of the filament based on the current flow through that. So, incandescent bodies are giving out a radiation which is dependent on the temperature which is maintained by them. The higher the temperature, you have the higher output. On the other hand, if you have any material, therefore, it means it needs to be operated at the highest possible temperature, and at the same time we do not want any evaporation of the filament material. Yes, it must be operated at a high temperature without causing any evaporation of the filament material. That is one important thing to be borne in mind. Having said so much, let us look a little more deeper into the physical processes that are enabling us to have various artificial sources. The first one, as all of us are familiar, in fact the naked lamps which are used by most of us are these incandescents. So, and the physical process that is responsible for radiation in these lamps is known as incandescence and is also termed thermoluminescence. This, as already brought out, depends on the radiation of light at the elevated temperatures. The filament is being maintained at a higher temperature, and in fact there is an associated heat. This has led to incandescent lamp which is normally used. The early days it used to be in the form of a gas lamp, or all of us are familiar that in our temples we light lamps using oil, or when power goes we use candles which are essentially depending on wax. Incidentally, it must be mentioned the standard of measure of light output is talked in terms of candle, and luminosity is luminous output is standardized as candela. Hence, this all gives rise to what we call continuous spectrum. See the beauty of nature. It is continuous just as it has been continuous due to the natural sunlight. So, that is the thing. In fact, all modern ways of looking at alternate sources is to get a similar continuous spectrum at optimized energy consumption at an economic price. The second part is second physical process that may be used is luminescence, and this is also called electroluminescence. In the sense, why it is called electroluminescence? It is because this is a form of a discharge obtained by the passage of electric current, and the discharge is of a particular radiation. Put in other words, this is a chemical or electrical action on a gas or a vapor leading to light radiation. Now, all these arc lamps which we have are the arc lamps used in projecting the motion picture. They employ carbon electrodes. There is an arc struck between two electrodes. The arc is essentially a combination of ionized particles, which is a vapor, which gives rise to radiation being at a high elevated temperature. So, we find that unlike the incandescence, this does not produce a continuous spectrum. It produces color of light of a particular color. Now, this color depends on the material employed, and therefore, on a spectrum, if you try drawing the wavelength vis-a-vis the radiation output, you find that it is not continuous over the entire visible zone, but it is discontinuous or is known to produce what we call line spectrum or line bands. This is why it is called line or a band spectrum. The next one is fluorescence. Who is not aware of fluorescent lamps these days? We are using fluorescent lamps extensively. In fact, next to incandescent, fluorescence is the most used source of light. This is the state of art as far as interior lighting goes. This is also termed as photoluminescence. In the sense, the concept is that there is a material that absorbs energy at one wavelength and radiates another wavelength. Mind you, we said the light can be categorized into three zones. One is ultraviolet, second is visible, third is infrared. Now, if a material is able to absorb at one wavelength and radiate another wavelength, you remember the spectrum we showed, the blue sky has a peak around 420 nanometers, but our eye cannot respond very well in those zones. Keeping that in mind, supposing there is a material that can radiate energy, maybe in the UV spectrum, and if there are materials available that can absorb the radiant energy and convert it and re-radiate at another wavelength which is in the visible zone, then we call this particular phenomena as fluorescence. In fact, the fluorescent lamps which we employ use this principle. They have what is known as phosphors, which absorb the radiation, UV radiation, due to a discharge in a low pressure mercury vapor, which is re-radiated as the visible spectrum. And in the process, we are able to get what we call as a cool light. Remember, when we use an incandescent lamp, it is not just the radiation alone, because the radiation is due to the filament being maintained at a high temperature. It tends to heat the environment. There is a associated heat. On the other hand, the amount of heat radiated in a fluorescent lamp is much less and efficiency is higher. Some of the examples could be the fluorescent oils. Uranium is one such material. Zinc is another material which is often used, and as already told to you, it emits a visible light in the visible spectrum. There is yet another physical process which is often used, but may not be directly, but this is what we call phosphorescence. We talked about energy absorbed at a particular wavelength and re-radiated in the visible zone, but there is no time delay. On the other hand, phosphorescence or chemiluminescence is what we call as a process by which radiant energy is absorbed, and having been absorbed is radiated at a later point in time as a glow. One wonderful application is in the highway system, where we use these kind of materials, and these luminous paints, they are useful for this particular purpose. And this, the advantage is they radiate. The difference between fluorescence and phosphorescence is this. In case of fluorescence, the source of discharge is there, only then visible spectrum comes out. On the other hand, a phosphorescent material, okay, does not require the original source of light to be available for radiation. Once exposed to light, it slowly radiates. That is why when the roads the roads where traffic density is low, they can be marked with such phosphorescent luminous paints, so you need not waste energy and they can give the thing. In fact, highway engineering is one place where these physical process is extraordinarily employed. Therefore, if you see, in effect, most of our applications use a combination of luminescence and fluorescence. Luminescence, as told to you, is a form of a gas discharge which is a line spectrum. Fluorescence uses conversion of UV or the conversion of radiation at one wavelength to the visible wavelength. Fluorescent lamp, luminescent source, low luminous value, activating fluorescent surfaces which lead to visible radiation. Intensity, of course, depends on the kind of gas that's used. Obviously, fluorescent lamps use, as I told you, low pressure mercury vapor. So, the magnitude of radiant energy will depend on the gas vapor that is involved, and how much of this UV light that is radiated gets into the visible spectrum is dependent on the phosphor material that's employed. Central to the whole thing is that radiation temperature is a very important issue, because that's been the primary this thing for the incandescent sources too. And even if you take luminescent sources, you will have an electrode that's maintained at temperature which creates the discharge and therefore radiation temperature. In this sense, it's necessary to define what is a black body. A black body, by definition, is one which is not transparent, which does not reflect but absorbs all the energy. Mind you, we are not talking about just light, all forms of energy, that is light as well as heat, and is known to follow what we call Stephen Boltzmann's law, which is shown here, which shows the radiant energy is proportional to fourth power of absolute temperature. Absolute temperature is in degree kelvins. If the temperature of the material is in centigrade, you basically add 273 degree Kelvin corresponding to 0 degree centigrade. W stands for the energy radiated output, then K is the Boltzmann's constant, which is 5.71 in 10 power minus 12. That's how it follows. In case the ambient temperature is T sub T naught, then the equation gets modified as shown here as W equal to K multiplied by T raised to the power 4 minus T sub 0 raised to the power 4 watts per centimeter square. Now, that means the radiated energy is proportional to the fourth power of temperature. Once again, quantifying or re-emphasizing that the higher the temperature, higher is the radiation output, and therefore efficiency is good at that time. Now, there is certain shifts in radiation maxima depending on certain issues. We will look into it. It must be mentioned the 43% of the visible energy is around the black body temperature of 6500 to 7000 degree Kelvin, and this is approximately the sun's temperature at 550 nanometers, that is corresponding to your relative energy maxima in the solar spectrum which we saw in the beginning, and this would amount to an efficacy of light output of 90 lumens per watt. It must be mentioned that for most sources, the light efficiency, the efficiency of radiation of the sources is talked in terms of the lumens per watt of energy consumed. Lumens, as we go along, will learn that is the way we talk in terms of the light flux that is radiated. Here this diagram shows the radiation spectrum for black bodies placed at various temperatures. We can see the curves given for 1000 degree Kelvin, 2000 degree Kelvin, 3000 degree Kelvin and 4000 degree Kelvin. As may be seen, for the curve corresponding to the body maintained at 4000 degree Kelvin, the spectral maxima is around 100 nanometers, whereas that for 3000 degree Kelvin is around 200 nanometers, and that for 2000 degree Kelvin is around 275 nanometers, and the 1000 degree Kelvin has around 400 to 500 nanometers. Another thing to be observed, higher the temperature, higher is the relative maximum energy. That is the two important issues. Therefore, there is a certain displacement, and this displacement of the maxima, we were talking about the displacement. The displacement is this displacement of the relative maxima, that is categorized or quantized in terms of Wein displacement law, where lambda m in the expression stands for the wavelength corresponding to the relative maxima, T is the temperature, and this product is known to be a constant, where T is the temperature of the black body in degree Kelvin. We saw, if you recall, we saw in this diagram, the black body maintained at various temperatures had different maxima. This occurrence of maxima at different points is what we call displacement, and that is quantized by the Wein displacement law, and it says it's a constant. This constant is known to be 2960 for a perfect black body and is 2630 for a platinum body. So this is by combining. We had equation 1, which was essentially Stephen Boltzmann's law, which showed how the radiated energy is proportional to the fourth power of temperature, and the equation 3, which showed the Wein displacement law, which says that the product of the wavelength corresponding to a maxima and temperature are a constant. Combining these two, one gets that Wm corresponds to the relative energy at the maximum lambda into T to the power minus 5 is a constant B. Now this constant is known to be 6 for most of the things. Now it's a time we define what is a gray body. Having defined a black body, we define the other end, what is a gray body. A gray body is one which radiates lesser energy than that in the case of a black body. However, one should bear in mind that the ratio of visible energy to the total energy is kept constant or remains same. That means a gray body is one which reflects a certain percentage of energy at each of these wavelengths or lambda. One good example of a gray body is a carbon filament lamp. When we study the incandescent lamps, will become clear that the first of the incandescent lamps had carbon filaments. So as opposed to black body and gray body, we have what are called selective radiators. So, selective radiation means radiates less total energy compared to a black body at the same temperature, but it does radiate more energy at certain wavelengths. See, a gray body reflects a certain percentage of light at all lambdas. On the other hand, a selective radiator radiates more energy at certain wavelengths, not all. And if supposing the lambda or the wavelength at which it radiates more energy is in the visible region, it will be useful for us as a source of light, artificial source of light. And one such example are arc lamps. Now, having said this much, it becomes necessary to know how we categorize sources in terms of what we call color temperature. So, we have seen that a material being maintained at a certain temperature is central to all kinds of sources. The four processes we saw were what? Thermoluminescence or incandescence, electroluminescence or basically a discharge lamp, fluorescence, absorption of energy at a particular radiation of energy at a particular wavelength which is converted into visible spectrum. The other hand, the phosphorescence, radiation at one particular time is re-radiated at a later point in time. So, and this can be compared in terms of a black body radiation, and therefore we define what we call a color temperature. This is that temperature at which a complete radiator, we said a black body, must be operated to match the color of luminous source. So, whatever source we have, when we say it has a certain temperature, 1000 degree Kelvin as color temperature, it does not mean that it is going to be operated at 1000 degree Kelvin. It means that if a perfect black body is taken, it needs to be operated at that temperature to get the same radiation output. For instance, the blue sky, which is all pervading, can be thought of having a temperature of 25,000 degree Kelvin, whereas a fluorescent lamp, typically what we normally employ, has a temperature of 4,500 degree Kelvin. The daylight, what we have 500 watt daylight lamp has a 4,000 degree Kelvin, and similarly the candle flame, which we are very familiar, has a temperature of 2000 degree Kelvin. Now, this picture in fact shows on one side you have three columns. In the center we have the temperature scale in terms of a color temperature. On the left hand side it talks about the natural sources. On the right hand side we have artificial sources. We said artificial sources could be using any of the physical processes such as incandescence, electroluminescence, fluorescence and phosphorescence. As may be seen, between 24,000 to 28,000 we have on the left hand side extremely blue clear sky, whereas on the right hand side we have what are called as a daylight fluorescent lamp, okay. And likewise, if you go down, you have blue northwest sky between 18,000 to 22,000 degree Kelvin, and with thin clouds the temperature comes down to 12 to 16,000. Now, here on the right hand side you should observe that a single source is not mentioned, a combination of sources are shown. As may be seen, in order to get radiation in the zone 22,000 to 28,000 degree Kelvin color temperature, we have to combine more than one source or use certain filters. As can be seen, completely overcast sky, uniformly overcast sky can be compared to a daylight fluorescent lamp which may be having around 5000 degree Kelvin. Continuing further, average noon sun can be seen to have around 5500 degree Kelvin, which can be obtained with a one fluorescent lamp maybe. Okay. So, this is how the as we go along we see different kinds of lamps, 500 watt daylight photo flash lamp, 150 watt lamp. All lamps, as we go further down we find this thing, and how the natural light and the artificial light color temperatures are going around. You can also see the range of gas filled and vacuum. As we go, we will see that the incandescent lamps which are put in a bulb or an envelope, glass envelope, could be evacuated or could be gas filled. The gas filled lamps come in the range of 3000 degree Kelvin, whereas the vacuum lamps come around 2500 degree Kelvin. So, around the sunrise the radiation is known to be around 2000 degree Kelvin. So, having seen this, what have we learned in this lecture? We have learned that light is the radiant energy that provides visual sensation. We have seen how the spectral energy is radiated, and it has a maxima around green yellow zone, and the entire light output can be categorized into three regions: 1 ultraviolet, 2 visible zone, 3 is the infrared. And we also seen that human eye responds between 380 nanometers corresponding to violet to 7 nanometers corresponding to red, with a maxima around 550 nanometers, coincident with the maximal radiant energy due to sun. Maximal relative energy content of sunlight and maximal luminosity of human eye, as already told to you, both are around 550 nanometers. The artificial light sources, as we know, are incandescent lamps and gas discharge lamps. And continuing with the summarization, we have seen that the processes that could be employed in the artificial lighting are incandescence, luminescence, fluorescence and phosphorescence. As told to you, incandescent lamps are commonly employed. Luminescence is all the discharge lamps which we come across, the sodium vapor, mercury vapor which we see in our street lighting, fluorescent lamps commonly known as tube lights, and phosphorescence is employed in luminous signs that are employed on highways. And now, how does one obtain a good or efficient lighting? Is obtained by a suitable combination of incandescence, luminescence and fluorescence. Incandescence, though produces a continuous spectrum, has low efficiency. That efficiency of a light source is talked in terms of the light output per watt of energy consumed. Light output, as will be seen later, is talked in terms of the lumens. Light flux is talked in terms of lumens. Therefore, a source efficiency is talked in terms of lumens per watt. And the Stephen Boltzmann's law and Wien's law is displacement law for thermoluminescence are very important, and they state that the radiation output is proportional to the fourth power of the temperature. And therefore, in categorizing any light source, we talk of a color temperature, the temperature at which complete radiator must be operated to match the radiation of the luminous source. So, with this, there can be few questions that could be addressed to complete the lecture. The first question could be, what is the range of light, visible range of light? What is the maximal relative energy content of sunlight, or where is the maximal relative energy content of sunlight? Distinguish between incandescent and gas discharge lamps. Why is it necessary to operate an incandescent lamp at maximum possible operating temperature? State principle of working of a carbon filament lamp. State principle of working of an arc lamp. Now, some of the questions that were posed in the previous lecture, let us try to answer them. The first question was, why do we go for transmission of power at higher voltages? Because power losses on transmission lines are inversely proportional to the operating voltage. 2. What are the two ways through which power can be distributed? As already brought out, it could be through underground cables or overhead transmission lines, as told to you in the previous lecture. In thickly populated metros, we tend to distribute through underground cables, in sparsely populated rural areas through overhead transmission lines. How do you decide the distribution voltage for a particular area? As already told, sparsely populated short distances you can distribute at a low voltage, that is 400 volts 3 phase, whereas densely populated vast areas it should be at a higher voltage, that is 11 or 33 kV. What do you mean by 400 volts 3 phase in an Indian system? As mentioned, in an Indian system it means the supply is 3 phase, the voltage is 400 volts line to line RMS, and the frequency is 50 Hz. Thank you. When is the load balanced? When is the load balanced? When both the magnitude and phase of the load impedances for a 3-phase system are equal, the load is said to be balanced. As opposed to this, if either of them are different, then the load is said to be unbalanced. When do you go for a single phase and 3-phase supply? For single storied small buildings, one could have a single phase supply. For large buildings, 3-phase supply. That means when you have large loads, you need to distribute, you go in for 3-phase supply. Thank you.